the last two sections we're going to take a look at are 11.1 and 11.2. So 11.1 we'll do today, 11.2 we're going to split into 2 days. And they're on what we call sequences and series. So kind of the quick summary, a sequence is a list of numbers, and a series is when you add up a list of numbers. Okay? And for small sequences, adding up a bunch of numbers is easy, but if we had hundreds of thousands or millions of numbers to add up in a sequence, we don't want to do that by hand, and the goal is to figure out a quick way to do it. Right? So in order to be able to add up all the numbers in a sequence, we first have to be able to figure out what the numbers are in a sequence. Okay? So we're going to talk about some formulas we can use to find the numbers in a sequence. Okay, so a sequence of numbers is just a set of numbers with a specific order. Okay. Generally, there has to be some kind of rule for generating the numbers. There has to be a formula or a pattern or some set of steps that you're following to generate the numbers. We generally name a sequence with a lowercase letter. When we talk about a sequence, the first term in the sequence would be written using the lowercase letter for the name of the sequence and then a subscript with a 1. If you want to talk about the second term, you use the lowercase letter, that's the name of the sequence, and a subscript 2. Dot, dot, dot just represents there's some unknown number of terms between the fourth one and the nth one. But this particular sequence is finite, which means it has an end to it. Some sequences stop, some sequences go on forever. I know that this one stops because there's not a dot, dot, dot at the end. Okay? How many terms are in this sequence? That I don't know. But I do know that it stops at the nth term, however high that is. Now, when we are looking at the formula for a sequence, there's different ways we can calculate terms in a sequence. We're going to talk about 2 different ways. Okay. And I want to see, looking at this particular sequence before we really start getting into the formulas, to see if you can figure out a formula for the terms in that sequence. This particular sequence is infinite. Infinite means it goes on forever. And the way I know that is it has a dot, dot, dot at the end. Okay, so it never stops. Anybody think that they see a pattern or some way that you could describe to me how to get the next term in the sequence? Yep.
Could it be represented by 2 plus 3n?
Let's see, you said 2 plus 3n. So if you want to check if that's true, what I would do up above each of those numbers is just put in the position. Right? And now the n is the position. Okay, we're going to talk more about that. That's usually not the first formula people give me, but that's really good if you can think along those lines. Now, if I try plugging in n, let's try 1. If I plug in 1 for n right there, and I do it out, do I get a 2? Okay, so not quite. So it's along the right idea, but yeah, you want to refine it a little bit?
What if it was 2 plus 3 times the quantity n minus 1?
2 plus the quantity 3 times n minus 1.
Well, it's 3 times the quantity n minus 1.
Like that?
Yes.
Okay, well, let's try plugging in n there and see what happens. Well, if I plug in a 1, 1 minus 1 is 0 times 3 is 0 plus 2 is 2. Well, let's try 2. 2 minus 1 is 2. I'm sorry, 2 minus 1 is 1. 1 times 3 is 3. 3 plus 2 is 5. So it seems like it works. Try one more. Let's try 4. 4 minus 1 is 3. 3 times 3 is 9. And 9 plus 2 gives me 11. So with that particular formula, we could simplify it a little bit by distributing out that 3 and then combine like terms. So 3n minus 1. So the pattern here is if you take the position of the term you're looking for, triple it, and then subtract 1. That'll give you what you want to know. Right? So if you triple this, you get 9. Subtract 1, you get 8. Triple 4, you get 12. Subtract 1, you get 11. So if I wanted the 200th term, I could very easily figure that out. Triple it, 600 minus 1, 599. So the 200th term in that sequence would be 599. So that's a very good formula. That's the best way we can come up with a formula there. Does anybody see another pattern in the list of numbers there besides that one? I think this pattern's a little easier to see. Yep.
You add 3 from each one.
Okay, so you add 3. Can you say it again, what you're adding 3 to?
You start at 2, you add 3, you get 5. Then you add 3 to 5, you get 8. Then
Okay.
you add,
So in general, what are you adding 3 to?
um,
The previous term. So another type of formula that you could come up with is basically to say, I want the previous term, and I want to add 3 to it. Well, if this is the term I want, a sub n, how do you think you would represent the term before a sub n? Yep.
A sub n minus 1.
Yep, a sub n minus 1. And that formula works fine, but think about it with the example I just gave you, finding the 200th term. To find the 200th term, it says to take the 199th term and add 3. Well, do I know the 199th term from the ones they gave me? No. So now I got to figure out the 199th term. So the 199th term, fill in 199 for n, says to take the 198th term and add 3. That's how you get the 199th term. Well, I need the 198th term. Do I have that one? No. It's going to take a while. Okay, we're going to have to go all the way back to the beginning until we finally get to a term that we know, and then we can keep adding 3. Although this formula, most of the time, people give me this formula first because they see the pattern is adding 3. It is easier to see that, but that formula isn't as useful because it depends on the one that comes before it. So unless you know every single number up to the one that you want to find, this type of formula is not really that useful. So there's a name for each one of these. This one's definitely better. And we'll talk about each one. So one thing we have to kind of think about is when we're using formulas to describe terms in a sequence, we have to think about what kind of numbers you're allowed to plug in. Okay, if I was going to graph that on the calculator, like y equals 3x minus 1, I could plug in any number I want for the domain. But n here represents a position in a sequence. When you have positions in a sequence, that's very discrete. Right? There's nothing in between the first position and the second position. So plugging in a number like 1.7 for n, that wouldn't make sense. What would that even mean? You're trying to find the 1.7th term? There is no 1.7th term. So with these formulas that we're going to be working with today and pretty much all week, we have to understand that the domain is only positive integers. You can't even plug in like a negative 1 for n here. That would be like you're trying to find the negative 1th term. You can't. There is no negative 1 term. So the values you're allowed to plug in start at 1, and they go up from there. I touched on this a little bit, but there's two kinds of sequences we can look at. There's an infinite and there's a finite. And the difference is an infinite sequence goes on forever, which means when you're considering the numbers that you're going to fill in, right there in your formula, you can plug in every single integer from 1 to infinity. You can plug them all in if you're dealing with a infinite sequence. If you're dealing with a finite sequence, then that means it stops somewhere. So if we go back to this problem, let's say that there wasn't a dot, dot, dot at the end, and it actually stopped right there. That's the entire sequence, 2, 5, 8, 11. If that was my entire sequence, what would be the highest number I would be allowed to plug in for n?
Or
4, right? 4 would give us that. But 4 would be the highest number we're allowed to plug in. Yep. Any question why we couldn't go past 4 the way I rewrote it? Okay, so in that case, the domain is a subset of the positive integers. It's not all of them. It's just every number from 1 up to 4. And where it starts to get a little bit interesting, we're going to look at it tomorrow, is when you start adding up all the numbers in a sequence. If a sequence stops somewhere, you can definitely add up all the numbers in it. Okay? Even if the sequence had hundreds of billions of numbers, you can add up all the numbers. You can add up hundreds of billions of numbers. You can do that. But when we start to talk about an infinite sequence, and that's what we're going to look at on probably Thursday. In an infinite sequence, it is sometimes possible to add up all infinitely many numbers and actually get an answer, like 2 or 5 or something like that. So you might start to think, well, how could you add up infinitely many numbers? Wouldn't it just get infinitely big if you keep doing that? No, not always. Depends. So here's a pattern where they give us the formula for the pattern. And they want us to write down the first 3 terms and then the 15th term. Now, this is the kind of formula that you can plug in any number we want for n. We don't have to find all the ones that come before it. We can find any term we want directly. All right, so let's start with 1. If we plug in 1 into that formula, what's going to be our first term?
0.
0. Yep, first term is 0. How about if we plug in 2? What's going to be our second term? G? Yep, 1.5. I'm just going to leave it as an improper fraction just because it's a little easier for me to think about. But yeah, 3 halves, 1.5. How about if we plug in 3? What do we get? Yeah. 8 over 3. And what if we plug in 15? Yeah.
224, 225.
220
Oh, sorry, not 220, 224 over 15.
over 15. Now, if you start to think about those as decimals, you're going to notice that there is a pattern to what they're approaching. So 8/3, is that 2.6 repeating? So this is 1.5. That one's 2.6 repeating. And 224 divided by 15, 14.93 repeating. Anybody notice what those numbers are starting to get pretty close to? I mean, they're going to keep getting bigger and bigger, but if you look at, there is a pattern to what the number is getting close to. Yeah?
They're getting close to the value for n.
Yeah, they're getting close to the n value, which is the position. So the 15th term is getting pretty close to the number 15. The 30th term would be getting pretty close to the number 30. But it's always going to be a little bit smaller because of this -1. If the pattern was just n squared over n, well, then you could reduce that, and then it would just be n squared divided by n would give you just n. But in this case, the -1 changes that a little bit. Let's look at the other one. this one. Okay, before we start writing out the terms there, does anybody think they see what that negative 1 to the n is going to do? Yeah.
It's going to become like positive then negative, or positive then negative.
Yeah. This is going to cause what we call an alternating sequence. It's going to be positive. Every other term is going to be positive and negative. Okay. So we do the first term, negative 1 to an odd power. It's going to give us a negative. And then the second factor is going to cause it to double. So it's going to double and change sign each term. So negative 1 to the n. Negative 1 to the first is negative 1, 2 to the first is 2, then that one's going to be negative 2. Okay, the next one is going to be negative 1 squared, and then 2 squared. Right, so it doubles and changes sign. So negative 8. And what about the 15th term? Is it going to be a positive or a negative? Yep. Yep, it's going to be a negative because it's negative 1 to an odd power. And then we just have to figure out what's 2 to the 15th. Might seem like raising to the 15th power is going to be huge, but it's really not that big. So if a number is in the tens or hundreds of thousands, we'll write it down. If it said like 2 to the 50th power, no, I'm not going to write that down. That's going to be too big. We just leave it as 2 to the 50th. Okay, so that's 32,768. And that's a negative. Okay, any questions on that? So if you want to think about graphing a sequence, we can graph it, but remember when you graph it, you wouldn't want to make it a continuous, between on the graph. You can only graph discrete points. First term, second term, third term, okay, things like that. So let's take the sequence that we had before. And I think I remember the decimals. This is the n squared minus 1 over n. It's the one we did right here. So the first term, we got 0. Second term, when we got that, I think it came out to, was it 1.5? Yep, so 1.5. And we can't connect those two dots because there's nothing between the first term and the second term. Right? So those dots just represent the number in the sequence. Okay, the third term, I think, was 8/3. 2.6 repeating. And then when we got all the way out to the 15th term, I don't have enough space to do that one, but it was getting very close. I can do the 10th term. So that would be 99 over 10, which would be 9.9. Okay, so 5, 6, 7, 8. So 10th term, almost up at 10. So as we keep going with the dots, the dot is getting higher and higher towards the line that's above it. And eventually it's going to look like it's right on it, and it's going to approach it. Okay, so any questions on graphing that sequence? Graphing a sequence is just graphing dots. You can't connect them. So I told you there's two kinds of formulas that we can use when we're finding a sequence. Okay, one of them is called explicit, and the other one is called recursive. Okay, explicit is the one that's much better for us to work with. What an explicit formula allows you to do is find any term in the sequence you want directly. You do not have to find the one that came before it. So if you want me to find the 1500th term, I can find the 1500 term by plugging in the number 1500 in the formula. Now, if you compare that to a recursive formula, a lot of times recursive is easier to see, but it's not as useful. If you want me to find the 1500th term and you give me a recursive formula, well then I need the one before it, which is the 1499th term. But then to get that one, I need the 1,498th term. And I need every single term all the way back to the beginning. Okay, so recursive, a lot of chance to make a mistake if you're trying to find terms that way, and it's going to take a long time. So explicit is generally what we want. Now, for the kinds of sequences we're going to look at, the explicit formula is going to be relatively straightforward to figure out. There are some sequences where the explicit formula would be extremely challenging to figure out. We're not going to be getting into ones that are that level of difficulty. Yes? Yep. Okay, so looking at what I have here, does that formula look like an explicit formula or a recursive formula? Yeah. It's recursive. Anytime you see a formula that depends on doing something to the one that comes before the one you're trying to find, that is recursive. But when they give you a recursive, they have to give you one other piece of information. They've got to give you the starting point. And they can't just give you a formula without a starting point, because then you wouldn't know what the first value is. So in a recursive formula, how do I know the first value is 2? I would say it's given. It has to be given. The second value, I can figure that out using this formula. It says to find the second value, take 3 and add it to the 2 minus 1, to the one that came before it. Well, I know the first term is 2. So that's how I get the second term. It would be 5. Okay, and same idea for the third term. I would take 3 plus, using my definition, if that's a 3, a sub 3 minus 1 is a sub 2. 3 plus the second term is 3 plus 5. Any question on that? And recursive terms can get much more, recursive sequences or formulas can get much more complicated than that. I could give you one that's like something, let's say it's something like a sub n equals 2 times a sub n minus 2 plus 5 a sub n minus 1. So what that means to do is to get a term in the sequence, you have to double the term that came 2 before the one you want, and then add 5 times the one that comes immediately before the one you want. So that's a much more complicated recursive formula. And trying to change that to explicit, it could be challenging. It might be a quadratic pattern. We'd have to try to look at it and figure it out. All right, so in this one, they want us to determine the first 4 terms and the 8th term. So I made a table with all the position numbers. And what is the first term in this sequence? Yeah, 2. And how do you know? It's given. Yeah, the first term is a 2. And now what does the rule say to do to get the next term? You just had to explain that rule very, very simply to someone. Yep.
Take the previous term and add it by 4.
Yep, take the previous term and add 4. So what would my second term be? 6. And Nick, my third term?
Your third term. 10.
10. Travis, how about my fourth term?
14.
14. So they said to find the first 4, and now they want the 8th, but I can't jump to the 8th in this kind of pattern. I have to figure out everything that comes before it. Now it's only 4 more numbers down, so we could kind of figure out how many times you're adding 4. But just to get the idea of recursive, we'll just do them all in order. So my 5th term, Raj? 18. And then my 6th term?
22.
22. And Emma, my 7th term.
26.
6, and Vanessa, my 8th term. 30. So that's the one they really wanted. The 8th term and the first floor. Any questions on that? And if you notice, you are adding 4 a certain number of times to get to 8. Right? So you're adding it 1, 2, 3, 4, 5, 6, 7. You're adding 4, 1 less than the position you're trying to get to. All right? Plus the term you started with, which was a 2. So if we can kind of see that pattern, we can figure out a faster way to do this without adding 4 over and over each time. So now I want to see if we can do the same thing, but this time I want to change it to an explicit one. So if you want to write something explicitly, the first thing we want to do is try to change it to, first list the first few terms, look for a pattern, and then we'll try to change it. Okay, so first term here is 3. What's the next term? Yep. Yep, next term's 8. And the term after that? Yeah. 13. Okay. So what we want to try to figure out now, is there a way we can find a formula that you plug in a 1 and you get a 3. Plug in a 2 and you get an 8. Plug in a 3 and you get a 13. Anyone think that they see a formula? Yep.
5 and minus 2.
Let's try it. So multiply the position by 5 and then minus 2. 3 times 5 is 15, minus 2 is 13. 5 times 2 is 10, minus 2 is 8. 5 times 1 is 5, minus 2 gives you 3. So it appears like that formula works. In section 11.4, they prove it works. We don't do section 11.4. Okay, so 11.4 is a way to actually show that it works all of the time, because it's impossible for me to check every single number. How do I know that this formula is going to work when I get to the 3,467th term? Maybe it works for everything up until then, and then it stops working. Well, we can prove that it works all the time, okay, and that's called an inductive proof. But it's not something we're going to look at. Any question on that? So that's your formula. Okay, the next formula, this is another recursive one, okay, probably one you might have heard of. And it's not just depending on the term right before the 1, but it's depending on 2 before. So the first 2 terms are given. And can anyone explain to me what that rule is telling you to do? Add the 2 previous terms to get the next term. So what would be our 3rd term in this sequence? Yeah.
2.
Yep, 2. And you want us to go to the first 6, so we were halfway there. What would be the next term after 2? Yep. 3. And the next one? Yep. 5, and one more. Yeah. 8. Now, if I said to you, what's the 375th term? You're going to just keep adding them together like that until you get all the way to 375. It's going to take a while. But that one's not an easy formula to figure out explicitly. That's pretty challenging. So that is not something we would look at in this class. But it is possible to figure out a formula, but it's much, much more complicated than what we get. Okay, so that's called the Fibonacci sequence. It's the sum of the two terms that come before the one you're looking for. That's why they had to start you off with the first two. Now, this Fibonacci sequence, 1, 1, 2, 3, 5, 8, it comes up a lot. And we see it in different areas. Now, this is a special triangle. Does anybody know the name of this triangle? So that's called Pascal's triangle. And in Pascal's triangle, you basically add the two numbers above, and it gives you the number that's underneath. So like 1 plus 5 is 6, 5 plus 10 is 15, 7 plus 21 is 28. There's all kinds of interesting patterns in this triangle. If you look at a row that it has a prime number, okay, like row 5. This is row 5. What do you notice about all the numbers in row 5 that are in the middle? There's always ones going down the outside edges. But what do you notice about all the numbers in row 5 that are in the middle of the row? Notice anything about them? Well, what are the numbers? Yeah. What numbers are you looking at? And can you just say what they are? And what else? Anything that's inside the ones. What other number is there too? Yes, we have 5, 10, 10, 5. And we're in row 5. Okay. What do you notice about the numbers that are in between the ones? They're all, there's a special connection there to the row number. Yeah?
It's the same as the row number.
Well, they're not all 5s, because we have 5s and 10s in that row. Yeah?
They're multiples of the round.
They're all multiples of that row number, 5s and 10s. Now, the next prime number after 5 is what? Evan? 7. So look at row 7. And what do you notice about all the numbers in row 7 that are in the middle of? When I say middle, I mean in between the ones. Yeah?
They're all multiples of 7.
They're all multiples of 7. And that works for any prime row. Any row that's a prime number, all the numbers in the middle part of the row will be multiples of that row number. That does not work for other rows. Okay? Like if you go to row 6, not everything on row 6 is a multiple of 6. Okay. The other thing is, if I take these red lines and I put them exactly like that. And what I want to do is look at those diagonals, and I want to add up any time that a red line goes through the middle of a hexagon. I want to add up all the numbers that it cuts through the middle of. Right? An edge doesn't count, just through the middle. So look at that first diagonal right there. If you add up all the numbers that it cuts right through the middle of the hexagon, what do you get on that first diagonal? Lens? You get a 1. All right. Now look at the second diagonal. Add up all the numbers that second diagonal cuts right through the middle of. What do you get? Yeah, 1. You get a 1. Okay. How about for the next diagonal? What do you get after that? All right. you get a 2. So what you end up getting is the Fibonacci sequence. The next row, you would add up a 1 and a 2. That would give you a 3. And then a 1, a 3, and a 1. That'd give you a 5. All right. So that's just an example of where you see the Fibonacci sequence looking at those diagonals. Okay, and there's more we do with this, maybe not for you guys, but in section 11.3. This chart is also used in probability. What it basically tells you is the number, it tells you what are called combinations. Okay, it tells you about combinations. So like if I had these 3 markers, and I said to you, how many different ways could you choose 2 of them? Okay. 2 out of 3. Well, this chart would tell you, knowing that there's a total of 3 to pick from, and I'm saying you can pick 2 out of 3. If you went to the row and the column, row 3, because there's 3 objects, column 2, because I said you could pick 2, it would give you this number right there. That's row 3, column, whoops, technically it's this one, column 2. Right? Numbering is a little weird because the numbering always starts with a 0. So that's something, sometimes people get messed up with that. But this is column 0, 1, 2, column 3. Okay. So there's all kinds of different things you can do with Pascal's chart. All right, so we're going to look at 2 particular kinds of sequences that are very common patterns. One sequence is where you add a number over and over. Another sequence is where you multiply by a number over and over. The first kind of sequence we're going to look at is called an arithmetic sequence. Now you can pronounce it arithmetic or you can pronounce it arithmetic. It is correct both ways. I say arithmetic. So if a particular sequence is arithmetic, that means that there is a number that you are adding to get from one term to the next. And it has to be the same number every single time for the entire sequence. That number that we add, our book calls D, and it refers to it as a common difference. So why would you call something you're adding over and over a difference? Well, look at this pattern. Say I have 2, and I'm going to add 5 each time. So if I add 5 once, I get 7. If I add it again, I get 12. If I add it again, I get 17, 22, and so on. The way that you figure out what you added each time in an arithmetic sequence is you take a term and you subtract the one that comes before it. 7 minus 2 gives me 5. Do it again. Take 12 and subtract the one that comes immediately before it. 12 minus 7 also gives you 5. Take any term and subtract the one immediately before it, and that is how you can figure out what you are adding each time. If it comes out the same for every single pair of numbers, then you have an arithmetic sequence. And the pattern for an arithmetic sequence we kind of saw way back at the beginning. We saw it right there. Most people don't tell me that right away, but that is the pattern that we're going to look at. That is the very first term. That number right there is what you were adding each time to get from one to the next. And then I said that if you want to get to the 4th term, you have to add 3, 1 less than the number of times. Well, you have to add it for how many jumps you have to make. So if you're trying to get from 1 to 4, that's 3 jumps. So you add it 1 less than the term you're trying to get to. So we're going to write this down. We're just going to put it in a more general way. rather than writing it specific like that. So that's exactly the pattern that we had in the first problem. A sub 1 is the first term. And then whatever you're adding to get from one term to the next, add it one less than the number of times for the term you're trying to get to. You're trying to get to the 80th term, add it 79 times plus the first term, and that'll give you the nth term. Okay, so this formula takes all the guesswork out of trying to say, well, okay, maybe I times by 3 and then I add 6, or maybe I times by 4 and add 5. You don't have to guess when it's an arithmetic sequence. Find the first term, find the common difference, and then fill them in. And of course, n has to be an integer because it represents a position. You can't have decimal positions, you can't have 0 or negative positions. All right, so let's see if we can find an explicit formula for that. Now, that actually is impossible. What haven't I given you here that you would need to know to be able to do this problem? Yeah? Which term? Yeah, I guess technically I could give you any term because you could always work backwards. If I give you the 5th term and you know you add 3 to get to it, well, if you subtract 3 4 times, you could go backwards and figure out what the first term is. But I'll give you the first term. Say the first term is 7, and we're adding 3 each time. What I like to do is write out the first 2 or 3 terms, so then when I get my formula, I can check it and make sure it works. Okay. What's the first term in this sequence? Yeah?
7.
7. And Emma, my next term? 10. Jaden, my third term?
13.
Okay, let's go with that. Now let's see if we can come up with a formula, and then we'll check it with those 3. Okay. So based on what we had on the previous page, anyone think they could give me a formula for the nth term? Doesn't have to be simplified yet. Just fill into the formula I gave you. Yep.
3n plus 4.
And what is it?
Plus 4.
Can you give it to me just in that general format before we simplify it?
What do you mean?
So I want to plug it into that formula that we wrote down on the other page where it has the parentheses in it, and then we'll do the distributive property after to simplify.
Oh. 7
Yep.
n minus 1.
Plus.
N plus 1?
So 7 plus.
And 4. 7.
So there needs to be an n in it somewhere.
7 plus 4.
So it should have an n minus 1. And we should have parentheses, and then times d. So n minus 1, and then times 3. Okay, so that's your formula. Now you do want to simplify that as much as you can, but that's what you start with. What do we get when we just distribute and simplify all of that? Yep.
3n plus 4.
Yep, 3n plus 4. Okay, generally they're going to ask you to simplify it as much as possible, but start out with the version that I have up here, and then distribute, combine like terms, and get 3n plus 4. N is, I know I didn't really mention it, but n is kind of the letter they use when they're doing sequences. You could use other letters, but we're generally going to be using n. Any question on that one? Let's check it. Plug in the first term. 3 times 1 is 3, 3 plus 4. Yep, plug in 2. 3 times 2 is 6, 6 plus 4. Plug in 3. 3 times 3 is 9, 9 plus 4 is 13. So it does work for the first 3 numbers. Does it work for every single number? Well, that, again, that's an inductive proof. To show that, it's not something we do in this class. Okay, so next one. First 2 terms in an arithmetic sequence are given. Find the 5th term. So I want to think about this one by doing a formula, because it could just as easily say find the 5,000th term. Right? So having a formula is gonna make it easier. Okay. To write an explicit formula for an arithmetic sequence, what are the 2 things you need to know? Yep.
The first term and then the difference.
Yep. First term and the common difference, which you're adding each time to get from one to the next. What's the first term here? Let's negative 8. And what are we adding each time to get from one term to the next? Yeah,
6.
adding 6. Okay, so let's write down our formula. We don't have to simplify it in the first step. We'll do that in the second step. So what's my initial formula going to be? Yeah.
Negative 8 plus n minus 1 times 6.
Yes. Now, the way I'm teaching you to do the formula, I'm teaching you to do it with the first term. You can do it with other terms if you don't know the first one. We're not going to get into that, but it's just a small adjustment. Like if I give you a different term, we can still figure it out. But we're going to base it off the first term. So now we distribute, and we're going to get 6n, and then negative 8 minus 6 is going to give us negative 14. Question on that one? All right, so now let's try this one. Find an arithmetic sequence for this. So they give us the third term and they give us the 8th term. How could we figure out what we're adding each time to get from the third term to the 8th term? Yeah.
Divide the difference by 8.
So we do want to look at the difference. What's the difference here?
10.
10. And what do we want to divide it by?
Oh, sorry, not 8. It would be the difference in between the positions. You divide it by, in this case, 5.
5, right. Look at the difference between 13 and 3, and then look at how many jumps you make to get from 3 to 8. That's 5 jumps, and you have to move 10 units. So if you take 10 units and split it up into 5 jumps, how much is each jump? And be careful in this case because it goes from 13 down to 3. Yeah. Negative 2. Each jump is we're going down 2. So this would be 11, 9, 7, 5. But we really need the first term to use the formula that I gave you. So how are we going to work backwards to get the first term? Yeah.
You just add.
We just add 2. So going the other way. 15, and there you go. So now we know the first term is 17, and we're subtracting 2 each time. So the nth term is the first term plus n minus 1, and the common difference is negative 2. Okay, what do we get when we simplify that and combine all our like terms? Travis?
Negative 2n plus 19.
Yep, negative 2n plus 19. Let's just try one of them. Let's try the fifth term. If we plug in 5, negative 2 times 5 is negative 10. Negative 10 plus 19 is 9. And that's exactly what we have right there. Yep. Okay. Any question on that one? Okay, so the last type of sequence we're going to look at, sequence and progression, they mean the same thing, they're synonyms. So the last one is called a geometric sequence, or geometric progression. The difference with this kind of sequence is instead of adding or subtracting, you are multiplying. You always have to think of it as multiplying. So if you think, oh, well, I'm dividing by 2 each time, don't think of it as dividing by 2, think of it as multiplying by a half. Because 1/2 is the value you need in your formula. So always think of it as what you multiply by. Okay, so here's the general idea. To find a term, you take the term that came before it and you multiply it by a value. And R is called the common ratio. And again, at first it seems like, well, why are you calling something a ratio when it's a value you are multiplying by? Well, let's look at okay, look at that sequence of numbers. 3, 6, 12, 24, 48. If you're trying to figure out how you get from here to there, you take a term in your sequence and you divide by the one that comes before it. And there's lots of ways you can write that. This is one way. I could also write it like this. Take a term, and whatever you put in the top, just do a -1 and put it in the bottom. That's the same thing. So take a term and divide by the one that comes before it. 12 divided by 6 is 2. 48 divided by 24 is 2. 24 divided by 12 is 2. So that's called the common ratio. And now let's see if we can think of the formula a little bit. If I want to get from here to there, I have to multiply by 2 how many times? To get from this term, to get from the first term to the fourth term. Yep, how many? So how many times do we multiply by 2 to get from the first term to the fourth term? Yeah? 3. It's 1 less than the position number that you're trying to find. So how would we represent multiplying R by itself 1 less than the position we're trying to find? How would you write that down? Multiply R by itself 1 less than the position you're trying to find. Well, how do we represent multiplying R by itself over and over? What concept do we have to use? Oh, yep.
Would it be R squared minus 1?
So what are you doing with R? Can you guys describe it very generally? You're using the concept of
A power?
powers. Yep, so we need to raise R to a power. But what power would we raise it to if we want to multiply it by itself 1 less than the term we're trying to get to? It would be R to the Yep.
Minus one.
N minus 1. So you got to raise r to the n minus 1. Now, if all we did here, let's try that with 2. Let's raise 2 to the power. We're trying to get to the 4th term. If we raise 2 to the 4 minus 1 power, we get 8. We're supposed to get 24. So raising r to the n minus 1 power is only part of it. There's one other thing we have to do. Anyone have a guess what else we have to do? So instead of 8, we get 24. Something we haven't used that we're going to have to use in that sequence, and we used this in the last formula. When we wrote the arithmetic sequence, what are the two things that we had to know? Lens?
First term and the difference.
The first term and the difference. Well, this time we're not using the difference, we're using the common ratio. So we've already used the common ratio. We haven't used the first term yet. So what do you think we'd have to do with the first term? Yeah? Multiply it by what?
One by the first term.
Yeah, we have to multiply the result. When we do r to the n minus 1, we then have to multiply that result by the first term. And that will give us, in this case, 24, which is what we were looking for. So the formula is you raise r to the n minus 1. That takes care of all the jumps. But then you have to multiply it by the first term to get the correct answer. So it's a sub 1 r to the n minus 1. Okay, let's try this one. So it says find an explicit formula for the geometric sequence. Now, if it didn't say geometric, you wouldn't be able to come up with an answer here, because that formula could be arithmetic or geometric. When you only give me two terms, I don't have enough information to really figure out what's going on. But the word geometric, that tells me how I get from one term to the next. Okay. So what's our common ratio in this one? Lens? -2. Yeah. Common ratio is -2. So we know we're going to multiply by -2 n minus 1 times to get to the nth position. And what about my first term? How would we figure out our first term? Yep.
Divide the second term by -2.
Right, instead of multiplying by -2, we'll divide by -2, and that gives me a first term of
Positive 3.
+3. Okay, so now we get the two things that we need. We can fill them in. It's a sub 1 times r to the n minus 1. Question on that one. Okay, so that's a geometric sequence. So tomorrow, you're going to look at a series. So a series is when you take all the numbers in a sequence and add them up. Tomorrow, it will be all finite sequences, meaning that they stop somewhere. Thursday, when we get back together, we're going to finish up with infinite sequences. So remember, I won't see you tomorrow, and I won't see you Wednesday because of the schedule, but I will be here Wednesday, so if you want to come by, if you have a question, we can go over any questions, and I'll be here Thursday after school. Okay. So I will help you with 11.2 part 1, but you're going to have to watch the video, and you can work together on it, and I have faith that you can all figure it out working together. All right, so the homework, let's see, I could probably simplify that. 1 to 13 odd. So 1 to 13 odd, and then 14, 17 to 27 odd, and 31.